Jonathan, can you hear me? Okay, cool. How are you doing today?
I'm doing pretty well. How are you doing?
Everybody staying warm? I'm pulling up a couple of files that I'm going to need today. Okay. All right. Check-ins. How are you guys holding up in the cold? Good? Did you guys lose power yesterday morning? Yeah, amazingly enough, at my house, it's been on the whole time, but it was weird. I live 9 blocks away. I left my house yesterday morning, had power and got to school, and there was no power. And kudos to the janitorial staff. They were in White Science Center, in the dark, in the cold, cleaning the building. Amazing to see. Anyway, hopefully we're turning a corner on the whole cold thing. So hopefully life will be getting better over the course of the next couple of days. Do you guys have any questions over type 1 and type 2 error and how we use those things, how we think about those things? Okay, then we're going to shift into actually doing some statistics, which you guys are probably like, oh my gosh, finally we get to do some statistics. But here we go. We're going to start off with doing a set of analyses called chi-square analyses. I'm going to be flipping back and forth today between a PowerPoint presentation and working on my iPad. So there will be some transitions to deal with, but hopefully nothing too complicated. Also, something happened on Monday and it didn't record the lecture. So I'm checking right now and we are recording. Sometimes if I don't check it, it doesn't do it automatically for some reason. But yeah, we appear to be recording now. So I'm going to share my screen and what you should see at this point is, can you guys see my PowerPoint? Okay, all right. Yeah, not that again. Okay, so what we're going to be doing today is chi-square tests primarily. We might or might not get to test of normality. If we do, we do. And if we don't, we'll just cover that on Friday. The chi-square test material is actually found in your textbook, and this should be in the daily schedule. It is found at the very end of the book. So we're covering topics not in the order that they are in the book, but just covering them kind of the way I traditionally think of them. moving from analyses of nominal and ordinal data to analyses of continuous data, because most ecologists and biologists have to be dealing with continuous data primarily. In the textbook that I chose for this class, those types of techniques are at the beginning of the book. Chi-square tests and contingency tables, methods for analyzing frequencies are found in chapter 14. So chapter 14 is the section of the book that you should be using. So chi-square tests are tests that allow you to statistically analyze nominal and ordinal data, these types of data that occur in categories. Whether or not those categories can be ordered or not doesn't really matter. It's for this kind of categorical sort of data, colors, preferences, etc. And there are three types of chi-square tests, and I'll show you how to do each of these. The test statistic for each of these is all the same. It's a chi-square statistic, but the way in which you calculate expected values is differently for each of these. And that's the primary thing that you have to pay attention to. So there are goodness of fit tests where you test to see if the frequencies match some predetermined distribution. There are chi-square tests of homogeneity where you're just testing to see if the frequencies are the same across some sort of classification. And then there are chi-square tests of independence to see if cross-classified frequencies are independent of one another. And like I said, here you're just testing against some standard. Here you're testing to see if the frequencies are the same. And here you're trying to test to see if, for example, Democrats and Republicans might differ in their views on a particular topic or a particular set of topics. So we'll start with goodness of fit tests. So you guys probably haven't taken a genetics class, but in genetics, we teach students about these experiments done by this guy named Gregor Mendel back in the 1800s, where he bred peas. And the peas that he was breeding, when he bred them, they showed the phenotype, what the plant looked like or what the seeds looked like, appeared in different frequencies. And based on his ideas as to how genetics worked, he expected certain ratios to occur. So for example, with a single trait, he expected there to be at a 3-to-1 ratio of one trait to another trait. So 3/4 of the population should be one trait, and 1/4 of the population should be another trait. 3/4 of the population should be one trait, 1/4 of the population should be another trait. And so one of the ways to test to see if his idea was correct is to just by doing a simple chi-square test on this. So I'm going to do a new share and go to my iPad. Ah, there it goes. No, it is not going. Ah, here we go. So now I've lost my PowerPoint. Let me go get the data. So in that first example that we had, there were 5,474 round seeds, and there were 1,850 wrinkled seeds, for a total of 7,324 seeds total. And so one of the things that we could do is we could test Mendel's idea. Mendel's idea was that 3/4 of the population should be this type of seed, and 1/4 of the population should be this type of seed. So we can actually just go to our calculators. So pull up a calculator wherever you have a calculator with you. I'm going to do this on my iPhone. And we can basically take 7,324 times 3 divided by 4 equals 5,493. This is what we would expect if this population of seeds had 3/4 of the seeds being round seeds. And so we could do the same thing, take 7,324 seeds, multiply it times 1/4, and that would give us 1,831 seeds. We do the math here. They should sum to the same amount. So this is what we would expect if Mendel's 3/4, 1/4 hypothesis is correct. This is what we actually observed. So if we want to see if what he observed is different from what you might expect, you can calculate a statistic called the chi-square statistic. And the chi-square statistic is simply based on the observed value minus the expected value squared divided by the expected value. And then you add that up, so there's a summation out here in front. You add that up across all of the categories that you're dealing with. And so what this would look like for this particular example is we would take 5,474, which is the observed for the round peas, minus 5,493. We would square that difference and then divide that difference by 5,493, which is the expected. And then we would add that to 1,850 minus 1,831 squared divided by 1,831. Once again, that's the observed minus the expected. That value is squared divided by the expected. And then those two values are added together to calculate the chi-square. So 5474 minus 5493 is -19 squared divided by 5,493. And -19 squared is 361 divided by 5493, which is 0.06572. And then we would add to that 1850 minus 1831. That is 19, once again, squared divided by 1831. We square that, that's 361 divided by 1831. And we find that that is 0.434416, basically. Add that to 0.06572, and we end up with 0.50013637. Okay, so we'll just say that the chi-square is 0.5, which is not a very big number. As the expected values get further and further from the observed values, you would expect the chi-square to get bigger and bigger. As those differences get bigger and bigger, you expect the chi-square value to get bigger and bigger until finally it's big enough that you can say that those two distributions are not the same. So what we can do with that number now is we can go to the internet, for example, go to Dan Soper's website. So a website that you might find yourself using quite a lot is made by this guy named Dan Soper, who I think is freaking brilliant. Whoa, what happened? That did not take me to Daniel Soper's website because I wasn't looking at what I was typing. All right, search for Dan Soper, not Saper, Soper. So it gives you, if you type for Daniel Soper and chi-square, it gives you a couple of things to choose from. What we want to know is what the p-value is for a particular chi-square test. And in this case, the chi-square test that we have is basically a chi-square value of 0.5. And in this case, we have 1 degree of freedom because we have 2 categories. So once again, the number of categories minus 1 is what the degrees of freedom are. And when we click calculate, it gives us a probability value of 0.4795. So when we go back to what we were doing before, the p-value is 0.4795. And because the p-value that we calculated is greater than the alpha level, which is 0.05, we would conclude that these things are not different. So expected is not different from the observed. When we calculate a p-value in a p-value calculator like Daniel Soper's p-value calculator, what we're looking for is we want the p-value that we observe to be less than the type 1 error rate, because we don't want to say that 2 distributions are different from one another when they actually aren't. So 0.05 is once again the type 1 error rate. This is why we went through type 1 error rate last time, is so we would know where this 0.05 is coming from. We only want to say these 2 distributions are different from one another when they're not about 5% of the time. So the p-value is the observed type 1 error rate. And so this brings up an important point that we need to make. Alpha is the a priori type 1 error rate. It's the type 1 error rate that we say before we ever go and look at our data, we say we want to make a type 1 error rate no more than 5% of the time. So when we set this at 0.05, we basically say it's basically saying we want to make type 1 errors less than 5% of the time. Then we go and get some data. And when we get the data, we can calculate what the type 1 error rate is associated with that. And that appears as the p-value. And the p-value is the type 1 error rate for a particular test, a particular statistical test. And in this case, it was 0.4795. Is that right? Yeah, 0.4795. And what this basically says is we could say that the observed distribution is different than the expected. But, and now there's a big, huge but, if we did, we have a 47.95% chance of being wrong. And that's a pretty big probability of being wrong, saying that the two distributions are different when in actuality they're not. And we don't want to have that high a probability of saying that two things are different when they're not. And so because that is so high and so far away from our stated value of 0.05, we conclude they are not different. This is the conclusion that we reach because P in this case is much greater than alpha. Is that clear? Haley, it doesn't look clear to you. You have a this is not clear look on my face. What's up?
Yeah, I guess I was a little bit behind on your
I can't hear you.
notes, so I was like, can you hear me now, or you can't hear me?
Okay, hold on a minute. I still can't hear you. Somebody else try and speak to me so I know if my headphones are working. You guys can hear me, right?
Yes, we can hear you.
Aha. Okay, let's.
Can anybody hear me?
Now I can hear you. Okay, hold on just a minute.
Okay.
When you guys are silent the whole time, I can't tell if you're coming through my speakers on my computer or if you're coming through my headphones. And give me just a second. Let me see if I can. They were on. Okay, Haley, what's up?
Okay, I think I'm just confused in where you got the 0.4795.
Okay, so let's see, what's another way I can do this? So in the same way that we can go to a t-table and look up what the proportion of the density of a distribution is. So let me go back and share again. Every time I have to log out and in of the Wi-Fi in order to get my iPad to connect. Okay, so in the same way that we can look at a normal distribution and we can know from the distribution of a normal curve, we can know that if we come out a certain number of degrees of freedom, basically equal to t equals 1.96, that inside of this area, we will find 95% of the observations in that distribution. There's also a chi-square distribution. The chi-square distribution looks like a tailed distribution. And there's a certain chi-square value out here where we know that there's 5% of the distribution out here and there's 95% of the distribution out here in this area. And so, so theoretical statisticians figured all this stuff out a really long time ago. So one of the things that we can do is let's go back to the internet and just search for a chi-square table. So let's get rid of all of this. And so we can get a chi-square table, we can get a PDF of it, and this will just show us Lots of different chi-square tables. Can I make this thing bigger? I cannot make this thing bigger. Here we go. So this is a chi-square test like you would see in a statistics book. Can you guys see it on the screen? Yeah. And so what it's basically doing is it's structured in kind of the same way. Up here in the upper left-hand corner, there's an alpha level. And so it's showing alpha as you go across the table. And then there are degrees of freedom going down the column. And so what this basically says is if we want an alpha level of 0.05, which is right here, and we have 1 degree of freedom, which is what we have in this particular test, we have to observe a chi-square value that is at 3.841 or bigger before we'll say that that's a significant difference. Well, we didn't observe a chi-square value of 3.841. So another way of thinking about this is the chi-square that we need to observe based on the table value in order to say that two things are different is 3.841. Once again, based on getting a value from this table right here, okay? So this is kind of our rejection value. If we get bigger than this value for a chi-square, we can then say that those two distributions, the observed and the expected, are different. We actually observed our chi-square value is equal to 0.5. And so 3.841 is much bigger than 0.5. And so because the observed value does not exceed the tabled value, we would once again say that these things are not different. So we can also then go back to Dan Soper's website. Let's go back to Dan Soper's website, if we can. We could actually put in a chi-square value of 3.841. 3.841. And once again, 1 degree of freedom. And when we do that, you'll see that the p-value for 3.841 is 0.05. That's the 5% alpha level, the 5% type 1 error rate. So in order for us to say that two things are different, we would have something that was 3.841 or bigger as our calculated chi-square statistic for this particular data set. And in this case, we just don't. And the reason that we don't is because these two distributions, the observed distribution of 5,474 and 1,850 is just not that different from what we would expect if Mendel's idea was correct. So that's what that means. Is that making any more sense? Okay, let's do a data set that you're more familiar with. So we spent some time at the beginning of the class talking about the PRISM data set. So let's go and revisit that. So what we had in the PRISM data set, let's just do the data for Missouri because the numbers are smaller. We basically had prisoners divided by race, and then we had the prison population, and then we had the actual population of human beings in total. And so we had white people, we had Black people, and we had Hispanic people. And we had 20,565 prisoners who were white, 11,111 prisoners who were Black, and 593 prisoners who were Hispanic. And that adds up to 32,269 prisoners total in Missouri. And this is in comparison to a population of 4,866,980 white people who live in Missouri, 742,216 Black people who live in Missouri, and 263,909 Hispanic people who live in Missouri, for a total of 5,855,105. And the question that we have when we want to evaluate these numbers to see if the prison population is distributed unevenly compared to the raw population is we can calculate the frequency of each of the populations. So if we take 4,866,980 and divide it by the total population, what we find is that roughly 83%, 0.83124, 83% of the population is white, about 12% of the population, 12.369, is Black, and about 4% of the population is Hispanic. And when you add this all up, this should sum to 1. If all things are working out well. So what we can then do is we can take 0.83124, multiply it times the total prison population to ask ourselves, what is the expected prison population that we would see in prison if white people were in prison at the same rate that they are in the broader population? So we can calculate the expected frequency by taking the population, the prison population times the frequency of people in the broader population. And so when we do that, we end up basically getting 0.83124 times 32,269. That gives us an expected value of 26,823.19 people. When we do that for Black people, this 12% times 32,269, we should expect to see about 3,991.34 people in jail, and this 4% times 32,269, we should expect to see about 1,454.47 people. And when we sum that up, that should sum to 32,269. And unfortunately, I've done this in a Excel file, so there may be some rounding error. Is that about what you guys got?
How did you find the expected error again? Oh wait, was it the same?
You take
Never
the
mind.
frequency for the white people times the number of people in prison, the frequency for the Black people times the number of people in prison, and the frequency for the Hispanic people times the number of people in prison. And so that's why this number should add up to this number. And so let me do the math real quick on my own calculator. Yeah, it adds up. I got 32,269. Okay, so now you're kind of comparing apples to apples. You're basically saying we have one prison population made up of what you would expect the prison population to be if the number of people of these different races were in prison at the same proportion that they are in the broader population. And we compare that to the number of people who are actually in prison. So Haley, did that work out for you? Okay. So now what we're going to do is we will calculate the chi-square value. And in this case, the chi-square value for white people, it would be 20,565 minus 26,823.19 squared divided by 26,823.19. We would add to that the chi-square calculation for black people, which would be 11,111 minus 3,991.34 squared divided by 3,991.34. And then we would add that to the Hispanic numbers, which would be 593 observed minus 1,454.47 expected squared divided by the expected value 1,454.47. What that equals, and once again, I've done this in a spreadsheet. For white people, I got 1460.1139 plus 12,699.872 plus 510.24913. And our chi-square value, when you add all those things up, is gigantic, 14,670.228. Give me a little thumbs up or raise your hand or whatever when you're finished making those calculations. I realize I'm probably moving through this faster than you are. Chance, your eyebrows look very intense when you're doing calculations. Like you're totally in the zone.
Thank you, I guess.
Yeah, no, nice. No, I like intensity. Okay, Chance is done. The rest of you give me indications when you're done. Haley is done. Hayden is done. All right.
Did this. You got the same numbers that I got? Is that correct? What's going on? Something happened to my mirroring. Yeah. So you guys got the same numbers that I got? Okay. So let's go back to Daniel Soper's website and let's put in our observed chi-square value. Our observed chi-square value was ridiculously big, 14,670. Let's just round up because it doesn't really matter. With 2 degrees of freedom because we have 3 categories, and 3 minus 1 is 2, so it would be 2 degrees of freedom. And when we calculate that, it says the chi-square value must be between 0.0001 and 1,000 in order for Daniel Soper's website to calculate a p-value. So we observed a chi-square value that is so extremely large, out of the park, ridiculously large, that his chi-square calculator doesn't even return a p-value. So it's kind of the equivalent of saying it's a p of infinitely, ridiculously small. So that means that the distribution of what we observe in prison is so far out of whack from what we would expect based on the population that Daniel Soper's website won't even calculate a p-value for it. And so these distributions, the distribution of the prison population versus the actual population, are really, really different. Which is kind of what we already knew. Not only are they really, really different, you see that the biggest contributor to the overall chi-square value, so of this 14,670 value that is the chi-square that we observed, 12,699 of that is due to the discrepancy in the Black population in terms of the number of Black prisoners versus the expected number of Black prisoners that you expect based on their population. The next biggest discrepancy is in the white population, and then the smallest discrepancy is in the Hispanic population. So in this case, there are many more Black people in prison than you expect based on their representation in the population, and there are many fewer white people in prison relative to their proportion in the population. And we can calculate that by just looking at the difference between the expected value and the observed value. And so we see that there are about 6,258 fewer white people than we would expect, and there are about 7,119 more Black people than we would expect. So there's a negative deficit. There's a fewer white people, way more Black people, to the tune of 6,258 and 7,119, which is just the difference between what we see in the observed population minus what we would expect in the expected population. If the assumption is that white people, Black people, Hispanic people do crime at the same rate, and that's an a priori kind of hypothesis. Haley, does dealing with data that you've already seen, does that make the calculations make a little more sense?
Yeah, I think so.
Okay, then let's do another one. The way you get to know how a statistical test actually operates is by doing practice problems. And so that's what we're doing here. So we also had US data. So in the US, we had white people, Black people once again, and Hispanics. We have the overall population in prison. We have the overall population once again. The prison population for white people is 499,800. Once again, these are Department of Justice figures, which are strangely and oddly all ending up in rounded to the nearest 100, which makes me question their veracity, but I'm just going to go with it. 592,900 prisoners that are Black, and 330,400 prisoners who are Hispanic. That's set against a population of 4, well, let me go back. 241513942 when these data were collected. 3394787 and 33081736. So $241 million white people, 33.9 million black people, and 33 million and a little more than that Hispanic people. So take a few minutes, calculate what the frequency of the population would be. From that, calculate what the expected value would be, and then calculate chi-square. Let me know when you have these numbers written down, because I'm going to take my screen off while I do the calculations, and I'll be working on the calculations while you work on the calculations. Everybody have the numbers written down? Okay, all right.
I'm a little stuck. I don't remember how to find the frequency.
Yeah, so you would add up the population for all three groups. So add the population of white people plus black people plus Hispanic people. That should be about 308,543,515 individuals. And then you divide the number of white people by the total population, that gives you the frequency. Divide the black people by the total population, that gives you that frequency. Divide the Hispanic population by the total population, that gives you that frequency. Those frequencies should add up to a total of 1. So you can check your math by just adding those up. They should add to a total of 1. Get you on the right foot?
Yes, thank you.
Okay.
Can you go over how to calculate the frequency again? Because so far all my numbers are wrong.
Yeah, so you basically add up the entire population, which would give you the total population. Then you divide 241,513,942 by the total. That should give you the proportion of the population that is white, which is about 78%. White people. Divide the number of black people by the total population. That should give you about 11% black people, and then divide the number of Hispanics by the total, and that should give you about, once again, 10.7%. Who was that?
Me. Thank you.
Okay. So this is what I got. As you finish up, check your work. When I got to the chi-square calculation, just to save some space, I rounded, but it shouldn't make your numbers all that different from mine. Raise your hand on the Zoom call thingy when you're done with your calculations.
Did you say to find expected, you take like the prison population divided by frequency or something like that?
No, you multiply it times frequency. So you would take, for white people, if 78% of the population is white, then you would expect 71% of the prison population to be white. So you would take the frequency of the white people times the prison population to get what you would expect to be in the prison if white people were represented in prison at the same rate at which they're represented in the population. So frequency times prison population. For white people, frequency of black people times prison population to get the black prison expected, and frequency of Hispanics times the prison population to get the Hispanic expected. Hannah, when I'm done today, when I'm done teaching my other class, I'll post a PDF of my handwritten notes so you guys can have that just like I did the other week. I did it last week also. I just saw you take a picture of the screen, I think. So Haley's done. Logan looks like he's still calculating. Is everybody else still calculating? Hayden's done. Jonathan, you done?
Give me like one more minute and I should be
Okay.
done.
That's fine. Can you guys see an Excel file now? Okay. All right, is everybody done? All right, good. So you can also do this in an Excel file. I've made you do the calculations by hand because I think that's one of the best ways to learn how to do it. But you can also do this by in an Excel file much easier. So here I have the Missouri data up for you. And so you just take this and you sum across the different rows, take the population data, and then sum across those rows. You can get the percentage of the prison population by just dividing the prison population by the total number of prisoners. And you can do that for each of those things. They should sum to 1. You can get the percentage of the population expressed as a frequency divided by 1. Once you have that, you can multiply. In this case, the frequency of the population times the prison population total to get the expected number of white people. You can do that again for the black people, and you can do that again for Hispanic people. That should once again sum to the total. So these two sums should be the same. Expected should always sum to the same amount as your observed. You can then write in a little formula to calculate the chi-square, and you can see this is just F2, which is the observed, minus G2, which is the expected, squared. All that in parentheses divided by G2, which once again is the expected. Do that for whites, blacks, and Hispanics. Add that all up, and then you compare that to a tabled value of 5.99, because when we go to the internet and find a t-table, if we go down to an alpha level of 0.05 and 2 degrees of freedom, it's actually 5.991. And obviously, 14,670 is way bigger than 5.991. So this value, this distribution of expected is very different from this distribution of observed. We can actually calculate those discrepancies and basically see that there, at least in Missouri, are way fewer whites and Hispanics than you would expect based on population, and way more black people. When we look at prison, it's the same deal. You have your totals, you have your percent in prison, you have your percent in the population. You can see that there's 35% of the prison population is white, while 78% of the population at large is white. So that's a pretty huge discrepancy percentage-wise. But what that means in terms of the observed values compared to the expected is we observe a little fewer than 500,000 white people in prison, but if they were represented in prison at the same rate that they are found in the population, we would expect over 1 million people in prison to be white people. Once again, we can calculate the chi-square. The formulas are exactly the same as before. And we get this ginormous chi-square value, which is way bigger than the chi-square value of 5.991. And once again, we see when we look at the national data, there are 614,138 fewer white people than we would expect in prison based on population. There are 321 more black people than we would expect based on population, and 177,816 more Hispanic people than we would expect based on population. So this is how we would, when we were going through these data and graphing them before, I told you that there would come a point where we could actually do a statistical test to see if these distributions were actually different from one another. And this is the test that you would use for doing something like that. Once again, this is such a big number that Daniel Soper's website won't even take this number into account. And I've coded these as green and red based on whether it's better to be white versus black and Hispanic. Red is it's worse to be in these two categories, and it's better to be in the green categories based on the direction of the discrepancy between what we would expect and what we actually observe. So this is a chi-square goodness of fit test. It basically says, how well does the prison population fit with the overall population? That's why it's called a goodness of fit. And when we compare the observed to the expected, we find that the fit is not particularly good. The fit in the genetic data were actually quite good. They were not different from one another. In this case, they are very different from one another. And like I said at the beginning of the semester, you can have long sorts of philosophical and policy discussions about what's leading to this lack of fit, but statistically, the lack of fit is there, and it goes certain directions for certain groups and other directions for other groups. What you want to do about that, if anything, that's a different set of conversations. These are what the data show. Questions? Okay, on Friday, we're going to move out of goodness of fit test to test for homogeneity and test for independence. But once again, they all rely on comparing observed values to expected values. It's just a matter of how we go about generating the expected values. That's what changes the figure. It changes the chi-square calculation. So it's going to be the same equation, observed minus expected squared divided by expected, added across whatever categories you have. It's just a matter of how we calculate what the expected is. All right, then I will see you guys on Friday if there are no questions.
I have a question.
Yeah, Samuel.
Yeah, I sent you an email over the weekend, and you hadn't yet posted the lecture from like last Friday. Can you?
Oh yeah, it's up there.
Okay.
It should be on the. Yeah, I did that. Yeah, and the reason that Mondays isn't there is because Mondays didn't record for some reason.
Okay. Awesome. Thank you.
All right. Sure.